In the second presentation on data science for Shales, I will focus on spatial interpolation. So here we are not going to deal with specific covariates such as geological and completion parameters for each well. We rather look at an entirety of the production profiles over many, possibly thousands of wells, and to what extent we can interpolate spatially these production profiles over space. So we'll deal, of course, with creaking. Creaking is a method for spatial interpolation in general, but here we have to interpolate functions because we're dealing with decline. So there are really interesting methods to do that for functional creaking, and one of them is called trace creaking. So this presentation was of this presentation, yes, was also part of a presentation given at several places, as well as a paper that that I'll refer to in the end. And one of those was at the Petroleum Geostatistics Conference in 2015. And so I'd like to acknowledge the collaborators here, Alessandro Manifolio of the Department of Mathematics in Milan, and Ogi Grucic, who's my former PhD student. So I may have mentioned this already in the first presentation, but I'd like to recall a little bit the difference between conventional reservoir simulation, modeling, predictions, forecasting, engineering, and unconventional, the same unconventional methods or unconventional resources. So in the conventional resources, we typically build models constrained to seismic data, and then run flow simulations, do history matching, etc. So the time by which decisions are made is quite long, say, for example, or long term. For example, if I would like to develop an offshore platform, then obviously I'm going to do a detailed study related to where and how this platform is going to be built and what facilities I need to construct. This is very different in the shale environment where operators drill well at quite high pace. And so this idea of reservoir modeling and forecasting in a conventional sense becomes very difficult to apply. So here, for example, on the right-hand side, we are in the Barnett Shale, where we notice that we already have drilled several hundreds, if not thousands of wells. And the idea is simply, if I would like to drill a well in a new location, can I use the existing production directly without any reservoir modeling to forecast the production at that location? Let's now introduce some more ideas about the analysis of functional data and how we represent functions in space. As I mentioned, what we'll be doing eventually is interpolation of functions and not interpolation of scalars. So to do that, we have to define a proper space. The notion of Hilbert space is therefore introduced since it extends the concept of Euclidean spaces to spaces of any dimension. So, for example, instead of having a space on the vectors, we'll have spaces defined on functions. However, simply or similar to the definition of the classical Euclidean spaces, we'll have some analogy to that. So I'll introduce first again the idea of Euclidean spaces and extend that to functions. So we all know that Euclidean spaces of several dimensions here in 2 dimensions require definitions of operations, which are sums and products. So this is the classical algebra that you're probably familiar with. Then we also need to define lengths of vectors or norms. We need to define distance in that space. And so all this leads to the definition of the inner product. So what does that now do for functions, or what is the extension to functions? So now we're going to represent a Hilbert space of what is called L2, the space of the real valued square integral functions. So in this space, we're going to embed these functions. So for example, a point in that space, I'll put on my pointer. A point in that space here represents a function. A function is essentially an infinite dimensional object. So of course, as engineers, we are used to representing functions as discrete objects. That is not necessarily needed. In mathematics, it could just be an infinite dimensional object defined on the real line. So then, just like before, we need to define sums and products, and these are, in this case, pretty simple operations. So sum of 2 functions is defined here in that sense. Product of a function multiplied by a constant is also and that is also shown here. What's probably more interesting and important is to start looking at norms, distances, and angles. So the norm is the length of this vector, is simply then the integral of the square function. The distance between two functions in that space is defined as the integral of the square difference of these functions, and so on. So now we get a new definition of norm, distance, and angle. So what that will do to us later is that we can extend much of the mathematics and the ways of handling scalars into functions in a very natural and logical fashion. So what does that now mean for what we are doing? So remember that what we're doing is trying to, let me put up my pointer, trying to interpolate functions. So for example, if I have information at certain locations where I've observed a function, what would be then the function at that particular location where I have not observed a function? So you could say, well, there are ways around doing that without functions, and it is true, and I'll show in the next slide how you can just do the classical scalar methods. But you also see probably that there's some advantage of doing that with functions. So what we need the classical idea? The classical idea is to say, well, we have a space based on functions, so I can deal with that, so I need to create a space in which I can operate, and that was often done with projection or dimension reduction. For example, I can do principal component analysis on these functions and thereby define a principal component space on which I have scores. Then I do dimension reduction. For example, I reduce the dimension of these functions to 2. And so therefore, I map these functions into a two-dimensional space where I now have scalars, and then I just interpolate scalars. Of course, in doing so, there is possibly a there's a definition of when to truncate, that's the order of that space. And also, there's a loss of information related to that truncation, possibly. The other idea is to not do that and work directly or interpolate directly in that space of functions. So we're going to define spatial dependency not in R2, but in L2. We define creaking predictors, so spatial interpolation in L2. The advantage of doing so will show is that there's no information loss, and also we have to solve only one creaking system. On the left-hand side, of course, we are looking at solving creaking systems or estimation problems, linear estimation problems that are of multivariate nature. So here we'll still remain single variate. So just to give an overview of that, classical geostatistics versus functional. So, or give it the commonality here. So we assume that we have observed functions. These are these objects chi at locations S of some function. So this could be time or space. So in our case, this is time. And we'd like to use the classical geostatistical methods of variogram model creaking a function to extending that to functional data. So if we would do classical creaking, which means creaking of scalars distributed in space, we have to calculate typically the mean, or define, sorry, the mean of that scalar, which is expected value over that random function. And we calculate variograms. And here in the stationary sense, the variogram is simply the variance of the difference between any two observations, which is calculated using these expectations. So if we have already now defined for functions what are norms, distances, products, sums, etc., then we can extend this simple framework here of the scalar random field to a functional random field. So now I don't have scalars, but I have functions, so I can calculate the mean of the function, which is an expectation over these functions. This is the definition of that expectation. And we calculate what's called the trace variogram. You notice that the trace variogram, again, is the variogram defined of functions that are certain distance apart from each other. And since we have defined distances or differences by this least square this square norm here, remember that the distance between any two functions, which is the same as the distance, or is the equivalent that is here, the distance between these two scalars, is defined as this integral here. And so we get an immediate definition or an extension of this idea of the variogram to a variogram of these functions simply by using the distances as defined by these functions. So that means basically that now we've extended the idea of a scalar random field to a functional random field, and we can use exactly the same toolbox as we have in the classical scalar random field. So that summarizes basically the same idea. So in general, we would have interpolation of scalars. So we'd like to know what's at this location. Now we have interpolation of functions. So we are going to write a function as a linear combinations of other functions instead of a scalar, a linear combination of scalar. And so we need to determine these weights, and the weights will be determined using the classical creaking methods. So let's look at, for example, universal creaking. So in universal creaking, we are going to express our variable by means of a deterministic drift. So this is an unknown but deterministic drift. We don't consider this to be a random part, and some stochastic residual. And in universal creaking, we write this mean function here, this mean essentially as a linear combination of some basis functions. For example, if I have a trend in the x direction, this would be x. If I trend in both in the x and y direction, then these have two functions, x and y. And so then we use this framework to derive essentially we use this estimator, this framework, then to derive the creaking equations, which will come next. In terms of function, this is exactly the same. So we now have a deterministic drift function. So this will be a function and a deterministic stochastic residual. And so again, we'll write that deterministic drift function as a linear combination. Again, we have these functions f, but now our weights essentially are these unknown weights are also functions. So as you know, universal creaking problem, we will be minimizing the estimation variance. So the average square difference between the estimator and the true unknown under some unbiasedness condition. So without going too much into the details, this looks exactly like a universal creaking system. So in a universal creaking system, we'll get the components related to a matrix. This is the universal creaking system. We have the weights here, Lagrange parameters there. We have a matrix, and this is a vector. So we have a matrix here that is related to the variogram between any two data locations. In this case, these are functions. The evaluation of the trend in that of the basis functions at that location, and this is related to the variogram between the unknown location and any data location. So this looks exactly like the traditional universal creaking, and we'll solve it in exactly the same way. For more details mathematically on how we get to the system, we refer to this paper here, which is its reference is given at the end of the presentation. So just like rigging, traditional geostatistics, we need to evaluate the variogram. And so we'll use the method of moments, which simply says that we estimate the variogram using this simple average here, average over the number of lags that we have for those observations. So now, instead of a square difference between values, we have a difference between functions. And recall that the difference between function is calculated in this integral. And so now we need to think a little bit about approximations. And so typically what we do is we calculate this integral by discretizing the function and therefore approximating this integral in that sense. And that gives us this gives an estimator of the variogram between two functions that are at a certain lag distance away. Okay, so let's now look at an application. We'll be looking at, as I said, the Barnett Shale, which is in Texas near Dallas. What we have are, we have sorted some data as a data sorting that's going on, processing. We're not going to go into the details, but just say that we can deal here with a substantial amount of wells, whether you have 1,000 wells or 10,000 wells. For the method doesn't really make any difference. Actually, the more wells, of course, the easier to estimate the variogram. And so what we need to do, we have this data from drilling info. So this is monthly data, and so there's some noise to that. So what we do is we do some smoothing of those curves. And so each curve in this case is a gas production over time. So we're looking at here a production of 60 months. And so we have production, say, of 60 months over a series, a set of spatial locations. The question now is, if I like to estimate the production at a new location, what would that be and what would be its confidence? So here's an example of that smoothing. As I said, the monthly data has some noise to it, and we use functional data analysis to do that smoothing. And for that, I refer to the session 1 presentation on FDA, FPCA, etc. So in order to do some testing, we'll split this data set into 2 parts. There will be a training set on which we'll calculate variograms, etc., and that will be and do the creaking equations, set up the creaking equations, and then we'll do a test set where we actually have the true observation that we have observed in that field. So here's an overview of that. So we see here on the right-hand side some of the black are the training data, and some of and the gray are the test data. So our model is as follows. So we express our random field of functions as a deterministic drift and a stochastic residual. So in this particular case, we are using a linear model for the drift. So simply say that there may be some trend in the x direction and some trend in the y direction, which could be due to geological variation in the field that leads then to differences in production. So we have to estimate the trace variogram, and so if you are dealing with universal creaking, we basically have to estimate the variogram of the residual. And so here we see the variogram that's calculated based on that equation I showed in the previous slide. And so that's basically the same as the variogram that we would calculate for a simple scalar field. So that extends very nicely, and we see that indeed we get some range in terms of I don't think this is kilometers, it'd be meters or something else. And so we see that there's a specific range that is appearing. So, okay, then we can solve the creaking equations. We can predict directly the functions. You notice there's no basis decomposition, there's no co-creaking, so we directly predict the functions. And we can compare test set with the creaked functions. So, for example, a couple of examples here for this location. This was the actual production, so we got quite a good result. Here's some more locations. So overall, it seems we're not doing too bad. So in order to all summarize that in a performance measure, we will be computing the sum of squared errors, which is defined as this difference between the estimate and the actual observations. We normalize with respect to the variance of the process. So our mean SSE that is done over the entire test set is 12.5%. We can also obtain maps of the gas production for some interesting time points. So for example, I think these are actually the, so this is the time 60 months. So for example, I can also look at a map of time at T0 to 12, 24, and 48. So to do that, again, I don't need to solve for different creaking systems. I just calculate the estimated gas production rate curve, and therefore I can extract from that maps immediately. So here are some maps here. So we got the peak gas, of course, which is at time t is 0, and then we see a gradual decline. And so we notice that there's some areas indeed of relatively high production and areas that seem to have much lower production. So these are some, this is a different idea because this is a different color scale, so it conveys pretty much the same information. So let's make a comparison with other approaches, in particular the classical approach. In the classical approach, again, you would have the functions, you would represent these functions in some kind of lower dimension Cartesian space and then creating that Cartesian space. But since you're in higher dimensions, we need to do co-creaking and compare that with the trace creaking. So we do this, again, we do this basis projection, which is not needed in co-creaking. We do principal component analysis. For example, we can do functional principal component analysis and calculate scores. Of course, the question is then when to truncate, how to interpret these scores. It becomes much more difficult. So here is an example of the scores that we get from functional principal component analysis. So I refer again to the session 1 presentation on how we can calculate functional principal components. If I, for example, retain only the first two principal components, which in this particular case is 90% of variance, then I can calculate variogram of those principal component scores, and I need also calculate the cross variogram between those two. So this is fine if you have two dimensions or two variables, sorry, that can easily be solved. Of course, when you go to a higher amount of dimensions, you will need to invoke other creaking methods that have to deal with higher dimensional creaking or creaking of multivariate properties. For example, we'll have to use a linear model of co-regionalization, and we have to do substantial fitting of all these variograms. This is not needed, again, in the trace creaking approach. So the system you have to solve then, of course, is much larger compared to the system we have to solve in the trace creaking. So this is an example of that application. If we do the co-creaking, we get kind of something that looks quite similar. Again, with more modeling effort, slightly higher SSC than in the trace creaking. And that higher SSC may be due simply to either because we are truncating some of the data in terms of the information provided by the lower dimensional principal components, or we may have some stability issues when we're doing a linear model of co-regionalization and apply that to this interpolation. Another test set, again, we see some instability issues that are occurring. So you can also do a Monte Carlo study where we're varying the sample size and we are also varying the amount of percentage of training versus test set. And so in that Monte Carlo study, we can then look at the variation of the mean RSSC for various amounts of percentage of training sets. And we notice that consistently, the trace methods are outperforming the projection methods, although probably not by a whole lot. So in summary, I think we hope to have shown to you the idea of trace creaking or creaking with functional data in this particular case, which is a rather simple, efficient method to interpolate functions directly without looking at decompositions. And so we focused here on the universal creaking methods. Here are some references I'd like to refer to interesting papers related to the statistics of functional data, such as this paper here. Also the paper by Manifolio about the universal creaking predictor for spatially dependent functions in Hilbert space, and other papers related to that. Just as before, and this is the same reference I showed in the session 1 presentations, there is a number of codes that are available in R and other packages for you to try out some of these methods. Thank you for listening.